I'm Mitch Marks. I'm from HBK. For those of you who don't know, HBK makes precision sensors and data acquisition systems, as well as some software. So we like to think we have a really good knowledge on measurement and instrumentation. So without further ado, I will jump into the presentation. Quick agenda. I will go through this fast. We'll go through the basics of measuring voltage and current. You need that to measure power. We'll look at power measurements for both DC and AC. We'll talk about the averaging period, which is actually quite important for understanding and getting an accurate measurement for power. We'll touch on some sampling rate and filtering, which is a little more practical for those doing measurements. We'll talk about fundamental frequency and some notes on RMS, again, for those who really want to go down the rabbit hole. And we'll close out with measurement uncertainty and one slide on HBK's products. I lied, I have 2 slides on HBK products. Just so everybody knows, HBK makes power analyzers that can be expanded up to many channels. We can measure up to 1500 volts DC direct. We are extremely accurate for electrical power, and that's what I'm going to be talking about today, is how we actually measure power and how power is correctly measured. This is not a whole sales pitch, but there's a lot of math behind it. And then we interface with a number of HBK sensors, torque sensors, current sensors, and can bring in some mechanical measurements for things like torque, speed, vibration. So now to the part that you care about. So let's look at the basics of measuring voltage and current. So in our powertrain today, we all know this, but we have DC power measurements, AC power measurements, and mechanical power measurements. DC coming from that battery or power supply. AC is our 3-phase, 6-phase, pick your favorite number of phases, coming out of the inverter. And these are high frequency signals because that inverter is turning on and off at tens of kilohertz. We're creating sine waves at hundreds of hertz. Those are going into an electric motor, turning those electric currents, that high frequency AC voltage and current, into rotational energy, and that's going into a gearbox. So we got a lot of interesting stuff. We have this kind of static DC. We have this high frequency with multiple frequencies AC, and then torque and speed. So how do we measure these, and how do we do this correctly? And I think that's the question we want to answer today. So first of all, we need to measure voltage. You might say this is trivial, but again, when you're looking at power measurement, there's a couple of things that matter, and we're going to hear this over and over again. You have phasing, and you have reading range, but the phasing between the voltage and the current are very important. So when measuring voltage, you really want to measure directly. 1, because voltage dividers often introduce a phase shift, and 2, because voltage dividers or voltage probes often introduce an inaccuracy. So at HBK, we're able to measure plus or minus 1500 volts direct. If you really care about accuracy, you want to look at something that's in the range of like 0.02% or 0.00 something percent. And you want something that's differential. And the differential allows you to look at phase to phase or phase to neutral for 3 phases and keep them a common reference, but also keep the measurement system safe. So you usually want to look for direct voltage measurements to avoid phase shifts, and because it improves the accuracy. And it's pretty easy to do this for up to 1500 volts if you pay the money. Now, some of you might be going higher, and that's where they have things like 2 kilovolt or 5 kilovolt differential probes. Again, the issue with probes is that you start introducing inaccuracy. HBK offers a really nice 5 kilovolt probe that is quite safe. For higher voltages, you are going to have to find some sort of voltage divider. If you're going up to 20 kV or 60 kV, you might want to consider getting a voltage divider that's fiber optically isolated. Those are also things that HBK can offer, but look for a direct voltage measurement. It will help with your phasing and your accuracy. For currents, currents are probably the more difficult thing to measure. There's a few flavors of current sensor, but they kind of boil down to more or less 2 different flavors. You've got your flux gate based zero flux current sensors, These are really high accuracy. They have like crazy parts per million accuracy, but their bandwidth is limited. And when I say limited, I mean a couple hundred kilohertz. And we'll touch on this issue a little bit later in the presentation. There's some effort to install these. Like, you can't break that donut, so you actually have to disconnect the cable and run it through it. But that's at the cost of accuracy, or at the price of accuracy. It's extremely accurate. And these zero flux handle DC and AC. So that's really nice because you get the high accuracy on the DC and the AC with the same sensor. So these are the ones we usually advise for doing, performance and efficiency calculations. Now, sometimes you cannot break the cable, or sometimes you don't need that accuracy, or sometimes you just need crazy, crazy bandwidth. This is where current clamps or Rogowski coils come into play. These are all pretty low accuracy. And if you ever want to talk about DC clamps, like, those are the worst things on the planet for accuracy, but they get the job done. So clamps, usually low accuracy, usually have a pretty high bandwidth. A Rogowski coil has basically like an infinite bandwidth. Current clamps have typically a pretty high bandwidth, and they're very easy to install because you just clip them around the cable. So for we just need to get it done, current clamps, Rogowski coils are great. Rogowski coils are really good for getting into areas you can't usually fit. For the high accuracy, the characterizations, we advise the flux gate. Again, these have a bandwidth limitations. Sometimes they introduce a phase difference. Anytime you introduce a sensor, you're introducing more inaccuracy. So just some things to consider. All right. I decided to put sample rate and filters later in the presentation. We're going to talk about power calculations first. I'm not going to go into the definition of power or reactive power. If you want to get into that, we have a lot of videos on our YouTube channel. Please visit that or contact me after the seminar. I'd be happy to point you in that direction. So power measurements. All right. I want to start this with the problem on power measurement. So, when we're measuring power, we have the DC battery, voltage and current. We have the three-phase inverter. So I'm going to jump right into inverter-driven machines. And this inverter has this high frequency switching, several kilohertz. And it's this really high frequency, turn DC on, turn DC off, turn DC on, turn DC off. So it's got a lot of dynamics to it. Some of the newer silicon switches have really fast rise times. And this actually gets into the current. And we can see that there's this high frequency content in our current as well. So we have this high frequency AC voltage in blue. We have this high frequency AC current in red. These are inputs to the power calculations because, again, we're not directly measuring power, we're calculating it. And we have to ask ourselves, we all went to some sort of engineering college or went to high school, and we learned that power is voltage times current. And is it that simple? And you're sitting in this webinar, so you probably know it's not. So here's my problem. What happens when we just multiply these two things together? Well, let's look at instantaneous power, and maybe some of you have seen this. If we take that definition of power, P equals IV, we get a waveform that looks something like this. We have that high frequency inverter multiplied by that high frequency, the high frequency voltage multiplied by that high frequency current, and we get a high frequency power that has all of those dynamics and harmonics in it. And we can kind of see our sine wave of our current, ebbing and flowing. We can see that switching frequency. I think for an average power of something like, 5 kilowatts, we have peaks up to 15 kilowatts. We have negative peaks indicating there's a negative power flow at the switching rate. So this is not useful. This doesn't tell me anything about average power. This doesn't tell me much about, instantaneous power. This is just wild. This is nonsense. So instant power really is not useful. And I don't even know if you can think of it as being a useful thing because it's getting filtered by this machine. It's a nice thought experiment if you want to fall asleep. There's really no steady state value. You have these positive and negative swings, and it's at that inverter frequency. And you might say, well, that's just for the DC inverter or just for the AC inverter. What about the DC? Well, all of these harmonics are getting pushed onto the DC as well. It also has this high frequency content. So what are we to do? Do we filter this? Do we average this? What time period do we use for the averaging? Lots of questions come up when we think, how do we make sense out of this? So let's first look at the DC power example. Now I mentioned that these DCs connected to that inverter, that is not DC. You know, if you short a battery, you see DC, but the inverter draws a lot, and you get current ripple, you get voltage ripple. So the AC from the inverter is coupled to the DC from the battery or the source, just by the nature of we're turning this on and off very quickly. This high frequency content makes its way to the inverter. And again, we ask the question, do we filter this? Do we take an RMS? Do we take a mean? How do we calculate power? Because if we just take P times I, we're going to get a high frequency result again. So, all right, now we're going to get a little academic. I think this is where it gets fun and interesting. Let's take an example where we put 4 amps AC and 4 volts AC on top of 10 amps and volts DC. In red, I have my AC, 10 volts with, or 10 amps with a 4 amp AC coupled to it. In blue, I have a 10 volt DC with a 4 volt AC coupled to it. Now, let's look at a couple different methods. You know, if we take the average of voltage and current, so we take the mean, we're going to average out the AC. So if we look at the mean of our voltage and the mean of our current, you know, we get 10 amps because it averages out. Well, all right, let's take the RMS. The RMS includes that AC. All right, so we get, you know, 10.392. We get another different 10.392 for the RMS. Okay, cool. We have an average, we have an RMS. We now have a question. Do we use the average for power or do we use the RMS for power? Let's look at it. So let's take U mean times I mean. Well, there's no AC accounted for. So let's take U RMS times I RMS. Well, we forgot this AC has a phase component. What if the AC is phase offset? It absolutely could be. Well, by taking the RMS, we're not accounting for phase in the power. So if we look at our mean, we get 100 watts, 10 times 10. We look at our RMS, basically our apparent power, we get 108. But both of these are wrong. What we actually want to do is take the average of the instantaneous voltage times the instantaneous current. And if we take the correct measurement period, the correct averaging period, we get 102.7. So for DC or AC, we need to account for the phase, we need to account for the AC, and we need to account for the time period we're averaging over. So I think this is very interesting. This is an incredible problem. And if you're just filtering, you're losing all this information as well. So you really want to take the instantaneous measurement and average it over a period of time. Now, what that time period is something we'll get to in a moment. But if you take away anything from this whole presentation, power is the mean of U times I over a correct time period. That is the best advice I can give you for measuring electric power. The mean of U times I over the correct time period. All right, let's look at AC power and averaging period. As I just said, if you take one thing away, mean of U times I over the correct averaging period, what is that period? So again, this PWM inverter has these high frequency switch signals. Current is the result, so it also has a high frequency. So we just went over in the DC, you know, this motor is an inductor. This motor that this AC voltage is going into introduces a phase shift. So our voltage and our current are just by definition of going into a motor going to be phase shifted. So when we're measuring power, we need to consider what that phase shift is. We also need to consider, are we just looking at real power, or do we also care about reactive power and apparent power? Do we care about RMS? Because all of these things need an averaging period. You want to start really boggling your head and falling asleep at night, think about instantaneous reactive power. So we have to ask ourselves with this AC wave, what is our averaging period? How do we get P equals the mean of voltage times current? And I'm going to spoil my secret because there's no grand secret. It needs to be in an increment of sine waves. So you need to be an increment of these cycles or an increment of these sine waves. You can go as low as a half cycle or you can average as many full cycles together as you want, but you need to average power between the zero crossings of the AC. That's how we make sure we get phase accounted for correctly. That's how we make sure we get the right time period. And I'm not going to do an academic explanation of why. If you want that, we can take that offline. So let's look at, just some examples so you can really kind of feel what I'm talking about. Let's look at a voltage signal, and we're just going to look at RMS for now because the period for RMS and the period for power are going to be the same. Let's take an asymmetric voltage signal where we have just a kind of a half wave with a flat in the middle. And we're going to take two averaging periods. We're going to take a random averaging period, shown in black by this square wave, and we're going to take a synchronous averaging period. And we can see the synchronous averaging period. The averaging period starts at the half sine wave, and then it ends at the next half sine wave. So we're kind of locked onto this frequency. All right. So over the average, or over the random averaging period, we get a value that bounces around. We get positives, we get negatives, we get positives, we get negatives. And this is no good because what is our value? Is it this? Is it this? Is it this? Do I have to average this over a really long period of time? These are good questions. I know the answer. The answer is you use the right time period. By using the right time period, you get just a dead stiff measurement. And these are simulated signals. So this is really kind of the idealized world. But if you use the right period, you just get this totally flat RMS value. That's because we're not chopping off part of a sine wave here and getting a sine wave and a half there, or getting no sine wave in the middle. So this is a little bit of an extreme example. But if we look at that inverter, again, that inverter is a completely kind of asymmetric event. We don't want to chop off periods of it. We want to measure between the zero crossings. We want to measure a number of cycles. So again, if we look at that red, that just dead stiff, that super boring signal, we're doing that RMS over the whole asymmetric event. This red RMS measurement is just constant. Whatever time period I look at, I'm getting the value I trust. So this is what I'm trying to demonstrate, is that an averaging a random period, a wrong period, gives you bouncing wrong results. The right period, wherever you take it, is going to give you the right result. So between the cycles, mean of U times I over an increment number of sine waves. Okay, let's look at more of a realistic example. So let's take a real AC wave, and we're going to see much the same result. We take a random averaging period and we take a cycle-based period. Random black, cycle red. And we can see that these things look pretty similar, but they are not overlapping. And if we look at the RMS based on an average period, or RMS based on a random period, it's bouncing around. It's bouncing around the average. If we take the RMS on the correct time period, we get that dead stiff signal again. So again, just from the sake of getting a correct measurement, you need to use the correct averaging period. Now, there's also the question of filtering, and if you filter, you add phase shifts, and your results just go even worse. We will talk more about phase shifts in a moment. So not all time bases give a correct output. Only cycle-based or increments of cycle-based give you a proper output. And again, that RMS for the cycle-based is that boring red one. That's the right value. And the black one is a random time basis that's all over the place. And the reason I put this up there is if you're doing your calculations and you say, I'm just going to average over, a 10 hertz or a 50 hertz period, you're not going to get the right value. Or if you're filtering because you just want to filter it to a dead stiff signal, you're not going to get the right value. You got to do something like a cycle detection. Now let's look at power just for completion's sake. So we have a voltage and a current. They have a phase shift because we need to account for phase. We have that random averaging period. We have that cycle-based averaging period. And let's look at our reactive power. Again, reactive power, RMS times RMS. Apparent power. URMS times IRMS is my apparent power. It's how much there appears to be in the cable if there was no phase distortion. And as you might guess, our cycle-based period, the right calculation period is dead stiff, and the random period is bouncing all over the place. I apologize for the colors being wrong. Reactive power, we see much the same. And then the real power, we have this random averaging period. Oh, wow, I got the colors way wrong here. The random period is bouncing all over. The cycle-based period is dead stiff. And again, this calculation must be on a number of sine waves to get the correct result. Otherwise, it's just bouncing around. So cycle detection is the key to correct power readings. And what that looks like graphically, and this is a little bit of a sales pitch, obviously HBK uses cycle detection. It's fairly unique. It allows us to test very quickly and dynamically, which we'll see in a moment. But basically what a cycle detection is doing is it's identifying zero crossings in a sine wave, and it's saying, okay, I'm averaging over this time period indicated by the half cycle. Now, the way we do it is every half cycle, we do a calculation, and then we average the number of half cycles together that you want. But using some of the cool algorithms we have, we actually track that fundamental frequency. So as soon as you get to a measurement point, you can measure. Or if you're changing frequency, you get good measurements throughout that changing frequency. A lot of more traditional power analyzers use a phase lock loop, which needs a settling time. It can't do dynamics. It takes a long time to measure. And honestly, at high fundamental frequencies, they are quite challenged, whereas something like a cycle detect algorithm is quite good across the frequency range and as speeds are changing. So get the right number of cycles, use something like cycle detect if you want to be dynamic or test very quickly. All right, now the part that I'm probably gonna get, I've been a little excited the whole time anyhow. The part I'm gonna get really excited about is sample rate and filtering. I'm gonna try not to kill you guys with details. If you are interested, again, please reach out. These are like whole nother topics that I hope we can do with Mobex at some point. But for a general power introduction, I think they're also important because you have questions about power, you probably have questions about sample rate and filtering. So what sample rate do I choose? My inverter's at 10 kilohertz, my fundamentals at 100 hertz. Well, let's start to dig into that. For real power, this is power going to the wheels, power going to the torque. Fundamental frequency has most of a real power, but the rotational harmonics, the harmonics of the fundamental frequency, also contain some positive and negative power. So it gets quite exciting. We'll show an example of that a little bit. But the thing that does not contain real power is the switching. So the inverter switching does not carry power. The inverter switching is almost all losses. So that's one thing to consider. Real power going towards torque is in the fundamental and the harmonics of the fundamental, the 5th, the 7th, the 11th, the 13th. Your current sensor is often going to be the limiting factor for bandwidth in higher end instruments. So your current sensor might have again, coming back to talking about current sensors, a 200, a 300, a 500 kilohertz bandwidth. This is going to be your limiting factor. You can sample as fast as you want. That current sensor is going to limit your bandwidth. So catching the rising time, I get this question a lot. Don't I need to catch the rising time of my switch? Well, there's no power in the switch. You need to know when it turns on, but not really the details of it. Because the RMS is in proportion to when the switch turns on a very, very long period of time. So you don't need to catch the rise time because that real power is in the fundamental, it's in the harmonics. So for power, you don't really need that. For RMS values, just consider that like you don't need to go gigahertz to get a good power value. You need to know when the switch turns on. And if you do want to understand switching behaviors, you really have to go up to like hundreds of megahertz or gigahertz sampling rates. So it's just like kind of a fundamentally different test. So for power, your current sensor is limiting you, and the power is in the fundamental and the harmonics. All right, let's look at an example. And this is kind of busy, so I'm going to go slow. Here is an example where we have a simulated ideal signal coming from an 8 kilohertz inverter. So my voltages are in blue. You know, I have this idealized switches. My fundamental is 24.2 hertz fundamental. So we have my voltages up here, my currents down here. And we want to compare the sample rate of 10 megasamples per second and 2 megasamples per second with a current sensor that has a 500 kilohertz bandwidth. So we set this up in simulation. The measurement uncertainty of a real instrument is about 0.035% for power. And we're going to compare some filter rates. So we're going to compare some sample rates and some filter rates. What we're going to find out is that the filter rate is what really matters. So I actually put these in the wrong order. I apologize. So in our ideal system, the power is the same for each because that's our ideal system. So for the 200 kilohertz filter, which is actually what we're going to advise for doing these types of analyses, for the 10 megasamples per second, we see 2.139 kilowatts. For 2 megasamples per second, we see 2.3189 kilowatts. These are, you know, both like absurdly accurate. These are both well below the accuracy of an instrument. So if we look at the measurement chain for an instrument, these guys are in the margin. There's really no difference for that 200 kilohertz filter. And the benefit of a 200 kilohertz filter is we're allowing the switching, we're allowing a bunch of harmonics to the switching, but we're getting rid of all that higher end noise. And importantly, we're keeping it under the 500 kilohertz bandwidth of that current sensor. And the lower the bandwidth of the current sensor, the more true all of this gets. Now let's look at a 2 kilohertz filter. Let's say you want, like I want the fundamental. All right, cool. Well, 24 hertz, we're getting a lot of the rotational harmonics as well. 10 megasamples per second, 2.318 kilowatts. 2.318 kilowatts, these are the exact same number. I mean, really, really identical here. So again, we're seeing like almost the exact same number between the 10 megasamples and the 2 megasamples for a 2 kilohertz filter, which is still getting all of my rotational harmonics. I'm eliminating my switching frequency. And remember, this comes back to the fact that there's no real power in the switching. It's just losses. So if we're looking at real power, power delivered, that's all in the fundamental and the harmonics. Now, this is the one I like to include because I think this makes a crazy difference. If you have a different filter setting between, or let's say you just operate wideband with your instrument, and you're letting the current sensor be the filter for current, and the voltage has a much higher filter rate because your filter is significantly higher, you're going to see a big deviation in power. And now the percentage difference is 0.5% versus 0.6%. Yeah, the 10 megasample is better, but they're both very wrong. And that's because now with different filter rates between voltage and current, we're adding a ton of phase distortion. And this is going to be problematic for your power calculation because phase is quite important. The phase between your voltage and current is quite important. So filter at a rate that I like to include a lot of those higher end harmonics. I even like to set my filter so that some of my switching gets included because you're going to get just a super accurate result. So that's my thoughts on that. Care about your filter. Make sure your sampling is high enough that you're including your switching rate, but you don't need to go crazy. Your bandwidth is going to be limited by your current sensor. So some notes on sample rate. Useful power comes from the fundamental and its harmonics. The filters need to include the fundamental and its relevant harmonics, 5th, 7th, 11th, 13th. Some are going to cause positive torque, some are going to cause negative torque. I always like to advise sample high enough to utilize the full bandwidth of your current sensor. When current sensor bandwidths go up, we're going to see some of these things change, but right now that's our limiting factor. So, make sure you're getting a good measurement out of it. You want to sample high enough that you understand when that switch happens in your PWM, but it's not going towards useful power. So you're going to have to filter down because of your current sensors anyhow. We usually recommend about 20x your switching frequency for your sample rate if you want to get really functional. And just some practical tips: match your filters to your models. If you have a model team or you have a team running simulations, ask them what their filter rates are in their simulations. That will make sure your results at least have a chance of matching theirs, because those filters matter a lot, and we'll see that more in a moment. Use the same sample rate and filter for voltage and current. If you start mismatching sample rates or mismatching filters, you're just going to give yourself a really bad result. And again, your current sensor limits your bandwidth, so please note that. All right, fundamental power and notes on RMS. This is a passion project of mine because I end up comparing instruments a lot. It all comes down to filters. If you want to learn more, we have a full webinar we did with Mobex that I believe you can watch. All right, let's look at an example. I like examples. Here is an example of a voltage and a current with a 30-degree phase shift, fifth harmonic and seventh harmonic put on top of it. So it's just a simulated signal because it's clean and I like the example. So I get a lot of people asking about, these filter rates. What filter rates do I choose? Do I use a fundamental? And I like to just frame up why we consider using a fundamental and some of the challenges with using a fundamental. So for those of you who don't know, fundamental power calculation or a fundamental RMS calculation is just the fundamental. It's no harmonics, it's no orders, it's just the fundamental. So we look at our voltage and our current with our fifth and our seventh, and we see our power kind of swinging all around like a crazy man. And let's calculate our power factor. So our power factor calculated in kind of the traditional P over S is 0.827 for the full signal, and the fundamental is 0.865. Interesting. We have a big difference between our standard calculation and our fundamental. Now we look at our power, and I just told you that power doesn't have any switching in it, but power does have harmonics in it. Harmonics of the fundamental. Our power is 24.8 watts for the full mean of U times I over that cycle period. Don't forget that. Power is the mean of U times I over a number of cycles, 24.85. Well, our fundamental power, the power just from the fundamental, is 25.085. Why is my fundamental power higher than my power? Well, the answer is that the fifth harmonic has a bunch of negative power in it. But why are these different? Why are these different? That's the question. Again, I'm not going to kill you with math. That's not who I am. I like to kill with examples. So power is mostly fundamental, but some harmonics. Our standard RMS and our standard power equations include the fundamental and harmonics. And I think this is really important for the RMS and really important for reactive power, because your inverter is going to make these explode. The RMS and the inverter, if you're not filtering low enough, are going to make your RMS values explode. Fundamental is only the first harmonic. So when we look at the fundamental, we just look at that first harmonic. Fundamental RMS removes the harmonic content. So when people talk about phase, they almost always talk about the fundamental phase. When people talk about RMS, they're typically talking about the fundamental RMS. So if I look at my example here, same example I just showed, my full signal gets a measurement of 24 watts, 3.64 amps RMS, 8.25 volts RMS, theta 0.83, and apparent and reactive power of 30 and 16. Let's look at just the fundamental. 21 watts. That's quite a difference. The current RMS is actually quite similar, but still 0.1 amp off. The voltage RMS, pretty similar, but that's a volt and a half off. The power factor is different, and then the big ones are the reactive power and the apparent power are quite different as well. That's because the 5th and the 7th and the 13th and all of the subharmonics have content of those in it. So another big takeaway for RMS and those is when you're measuring and you're averaging over that number of cycles, I'm going to say this 1,000 times, measure over a number of cycles. You need to understand what you're looking for when you're doing a power, an RMS, a parent power, or a reactive power calculation. How many harmonics do I want included? Do I want my fundamental? Do I want my 5th? Do I want my 7th? Do I want to filter those out? Do I want to include them? You just need to know. So this comes back to the comment on filtering. How many harmonics do you want to include in your RMS calculations, in your apparent power calculations? And I will warn you, switching will make your RMS and reactive power numbers explode. They're just math. And if we remember back to that power, if we remember back to my instantaneous power with all that harmonic, that's getting into your reactive power. That's getting into your RMS. That's everything that's not real power. So it includes the switching. Real power, no switching. Everything else has that switching. So please mind that if you hook up an instrument and you get an absolutely gigantic RMS value, look at your filters. Look at what the filters of what you're comparing it to. If the model's got a low filter, you need to consider that. If a different instrument has a low filter, you need to consider that. So it's all math. There's only so many ways to fool Mother Nature. Let's look at a real signal. So we have a voltage waveform, we have a current waveform, we have our instantaneous power, that nonsense with all the switching. And so this is real data sampled at 500 kilohertz with a 50 kilohertz filter. Power is not affected by filtering, remember. We're taking the average. So there's a little difference if we compare, and then I'll walk you through this chart, is we have a 50 kilohertz filter, we take all our measurements, a 10 kilohertz filter, we take all our measurements, and a fundamental, we take all our measurements. So our real power is the same. Real power is a bit higher in the fundamental because there's a little 5th harmonic, but not much. We look at our current RMS, pretty much all the same. But like that's because we get a nice sine wave filtered by the motor. The motor's already acting as our filter. But our RMS values, our power factor, our S and our Q are drastically different. My VRMS is, 3x smaller for the fundamental. That's because the fundamental doesn't have those harmonics in it. It doesn't have the switching in it. Our power factor is almost unity, but again, 50 kilohertz is not. So again, for real power, we want that high filter, but for RMS, we usually want to talk about the fundamental. Same with reactive power. We need to know how much harmonic we want in the reactive power. 6.3 kilovar versus 113 volts amp reactive. Again, I say a lot of this to know that you need to know what filter you're choosing when you talk about RMS or when you talk about reactive power. Because for real power, we need to have those harmonics of the fundamental. For reactive power, we need to know what we're talking about. And we need to compare apples to apples when we're talking with teams that are doing modeling, when we're talking about teams that are making measurements. So HBK does provide fundamental equations. We try to make this easier for you, but you need to know what you're measuring because the math is math and it doesn't care what you put into it. Some notes on fundamental and RMS. When doing a power calculation, know how many harmonics you want to include. When doing an RMS calculation, know how much harmonic content you want to include. When talking about power factor, most people want the fundamental power factor, the phase-based. Consult your models when choosing your filters, or if you want a fundamental or not. Consult your filters when comparing devices. If you're getting wrong results, it's usually the filters. There's only so many ways to fool Mother Nature, so you really need to understand your math and understand what you're putting into your math. Math just does what math does. You got to understand what you're putting in. So that's my rant about fundamental and RMS. I think I've probably gone through a lot, but I want to mention dynamic power. So I talked about the half cycle measurement that HBK does, and half cycle is really the fastest way to get a power measurement, and often the only way to get a power measurement as speed is changing. So this is an example of starting an electric motor or starting an electric vehicle from stop. And the current kicks in, and we can see the cycle is indicated by this black square wave. And as that frequency is increasing, the cycle detection is increasing with it. And we get a nice trace for our power, reactive power, and apparent power. Now, if you were using a different method that didn't track the fundamental, if it just took a while to lock on, you're going to get a wrong result when you're calculating that power. Because if it's a fixed value, you're going to have a very wrong fixed value throughout. If you have some sort of tracking method that's slower, has a delay in it, you're going to get continuously wrong results. So for a dynamic test, for changing speed, for changing frequency, you really want to use something like a cycle-based method, something that tracks the period so you can get that correct measurement result. Because again, we want to measure increments of sine waves. So if you're measuring dynamically, just make sure whatever measurement method you use tracks the frequency and tracks the zero crossings, because otherwise you'll get incorrect results. And what's the importance of dynamic power? Well, when we do something like turn a motor on or accelerate, we get a little inrush current, or we get more current than we would during a steady state. So we see this spike in current, and we see this big reactive power and this big real power spike. Well, this is because there's a lot of stuff going on. We're introducing new losses, we're changing inertias. So if you don't track this and you don't record this, you're going to miss this type of data. So you want to have something like a cycle detect or something that tracks your frequency for when you're making, again, changing frequencies, starting currents, dynamic type measurements. And once you do something like a cycle detect, you can track, fundamental frequency throughout a drive cycle. And you can actually look at the energy consumption, the power consumption throughout something like a WLTP or a WLTC cycle, and actually accurately trust your measurements during starts, during stops. You can evaluate when your power is overshooting. You can evaluate how your controller handles events like hitting bumps. So there's a lot you can learn from doing drive cycle testing, and you can account for those losses in the dynamics. I think this is my closing, is measurement uncertainty. So we've gone through a lot. Power equals the mean of voltage times current over the correct period, which is in between cycles. Choose your sample rate and filters, but measurement uncertainty is where I close. And I always like to do measurement uncertainty with an example. Again, I don't like math examples. We got a math guy if you want that. His name's Alexander. We have an inverter with power input and power output. Again, ideal inverter, 500 kilowatts with a 95% efficiency. Our input power is 500 kilowatts. Our output is 475 kilowatts. This is our truth. So if we have a 1% error, 500 kilowatts plus or minus 5 kilowatts, 1%. 475 plus or minus 4.75, 1%. What are our losses? 25 kilowatts. Well, we have to add these two together. So my losses are 25 kilowatts plus or minus 9.75 kilowatts. This is an error of 39%. And if we take something like conduction losses, where we add even more in, this is ridiculous. I don't even know how to calculate that. It's not a reasonable measurement. So this is why measurement matters. 1% might be acceptable, but if you want to look at the difference, you want to understand your losses, now it's a differential. If you look at 0.1%, well, now we get plus or minus 0.5, plus or minus 0.75, 25 plus or minus basically 1 kilowatt. That's 4%. We can at least start to trust that. We can start to work with that. And it allows us to trust more things like conduction losses or iron losses. Because while we might have a large error, it's at least something we can trust. So if you want to trust your measurements, you must understand your measurement uncertainty. This is really key. And this is the error of your measurement chain. Again, this is something we could talk about offline if you're interested. And I basically frame up measurement uncertainty like this: is like when you start looking at finer things like losses, you want to know that you have a band of confidence in that measurement, because if you start having your confidence band be larger than your measurement, that's a useless measurement. Or now look at it like you're comparing two things, like your engineer compared a control technique or changed a control technique, and you want to compare, is method A better than method B? Well, that's a differential again. If my power output for B is within the measurement uncertainty of A, we don't know if we made an improvement. So just consider your measurement uncertainty. HBK offers a really nice tool for calculating your measurement uncertainty based on the accuracy of your sensor, your instrument, your reading, your range, your frequency, your phase distortion. These all contribute to measurement uncertainty. We have another full webinar we did with Mobex on that. I think we have an upcoming one with Mobex on that, so please tune in if you're interested. We give you a tool that makes it very easy. And lastly, I'm going to close with a little bit of a sales pitch. I mentioned some of the things we do. We have a power analyzer and data recorder we call eDrive, featured in the middle. We also have sensors, torque sensors, current sensors. We offer the really accurate flux gate ones. Our acquisition system does a cycle detect where we track that fundamental frequency. And we have a software for viewing your data. We make it really easy to collect electric and mechanical signals. We make it very fast and accurate to measure efficiency and power for doing things like drive cycles. The cycle detection allows us to do that. We can expand to many, many channels, so you make really big systems. We can record all of the data. Unlike a lot of power analyzers, we can record a lot of data. And everything we do is executed in the real time. It's all happening in hardware, so you can feed it back to an automation system. And in most markets in Europe, Asia, and the Americas, we have local application support and product training. So please feel free to reach out to us. And if there's any questions, I would love to try to answer. Thank you.